Hello, and welcome everybody to the final IHE Delft online seminar of this year. And the topic of today is hydroinformatics, artificial intelligence, and digital innovation approaches to water problems. My name is Maria Laura Sorrentino. I'm Alumni Relations Officer at IHE Delft, and it's my pleasure to organize this event for our alumni community and for the professionals interested in the topic we have covered through the year. So today I'm delighted to introduce the following speakers and extend my sincere thanks to them for joining us. But before introducing them, I would like to remind you to just write the questions on the chat and we are going to collect it. And after all the presentations are finished, we are going to pick it and just address the questions. And last but not least, my apologies for the mistake I made to include a link that is not the proper one to access the Zoom. And for that reason, is Maria Laura now because I put my link. So if you can change in the chat your name, it's fantastic. And without further ado, our first speakers will be Ioana Popescu, that is also an alumna, but is Professor of Hydroinformatics at IHE Delft. Her research focuses on national methods, aspects of floods modeling, and vulnerabilities related to floods, lakes, and reservoirs modeling and water supply systems modeling and optimization. She has two guests that also work at IHE Delft, Claudia Bertini, that is a researcher also in the hydroinformatics group, and she holds an MSc and a PhD degree in a civil hydraulic engineer, the first one, and environmental and hydraulic engineering, the second one from Sapienza University in Rome. And her background in hydrology has with experience in rainfall data analysis, rainfall extreme events, remote sensing, and hydrological modeling. And last but not least, is Aris Ali, a PhD researcher at IHE Delft and TU Delft, also part of the group of hydroinformatics. He is from Pakistan and his research focuses on surface, subsurface hydraulic logical interactions and modeling nature-based solutions for climate adaptation under the European Horizon 2020 project EIFEL. Please, Ioana, the floor is yours.
Thank you, Maria, very much. Hello, everyone. And we are very glad to welcome you. I'm privileged to have two guests, two extraordinary experts to present you together with me what we champion, the field of hydroinformatics. Claudia, Dr. Bertini is our expert in machine learning, mainly what we nowadays call artificial intelligence, which is much more broader. And Harris, who will soon have his PhD defended, will present his work in a project for his PhD. Let me start by losing the time by sharing our presentation. I will start with a full screen to share, and then we will do the now it can go into the in a second, because of all this on the screen, I cannot reach the okay, here we are, and we will put this, hide it down, and also this, we try to hide it. Okay. So as you can see, today we will show you mainly artificial intelligence and digital innovation, all related to water management. And what you see in this small drawing, we are trying to go from data through information and knowledge and to support decision making. And we hope that in the future we will be able to also define a very clear framework for a digital twin for catchments and rivers. In our work, we are trying to represent the reality which you have it in the left-hand side into the digital world, and to do it as smooth as possible without really not noticing the differences, but still learning a lot and representing the real world. We are in the age of artificial intelligence and digital innovation, and at our institute, we really consider that this relates to new ideas and a lot about technologies within the digital realm for improved efficiency. And last but not least, the novel ways to interact with stakeholders, which you will see in a way implicitly in our presentation. The three speakers of today, as Maria presented, are Dr. Bertini, Haris Ali, and myself, and we are trying to touch upon remote sensing to be used for lakes, water levels, for modeling, for mitigating conflicts, exploring new flood metrics using metrics from AI that were developed within the SEND project, AI for climate services in the CLINT project, and climate change adaptation in the IFA project. All are applications that were developed within projects at IHE. Hydroinformatics is actually useful. It's in the time of data and looking especially at all the disasters that are coming, droughts and floods one after the other, the climate change, the change in temperature. Then we ask ourselves how to take mitigation measures. And we look on availability of data from space, what you can see here, but also data collected by citizens with phones, data available through different sensors. They are all a lot and big, and they can help us in modeling, complex modeling, integrated modeling, and result models representing the reality will help us to analyze and inform society. And with that, society will be prepared and do mitigation. And this is a cycle that goes back and forth because whatever it is done needs to start again. So the first application that we are showing to you is developed within the Water Peace and Security project, and no work is done in isolation. So we are always working in teams, and this research that I'm going to present you is done with my colleagues or with MSc students, and you will see that in the with my colleague Dr. Janovsky, Dr. Veniger, and with three MSc students, Sharuni, Mutaz, and Krishna. So let's come back to the presentation. We are focusing now in this project in Turkana Lake, which is in Africa, shared between Kenya and Ethiopia. It's the world's largest permanent desert lake with a very big area of over 7,000 square kilometers. And it has an inflow from an upstream catchment that it is the Omo catchment, 90% coming from the upstream catchment. And as an outflow, it has only evapotranspiration. There are several challenges in that area because there are social problems, there are conflicts for water, there are climate problems, flood and drought, and the main problem is it is a data scarce area. There are hardly data available. So the main problem is the lack of monitoring system and the lack of data, and the extra challenges are that in that area, in the upstream catchment, I hope that you could all see the tip of my mouth. There are hydropower schemes and irrigation exploitation plans that will affect the inflow into the lake. And around the lake, in the Turkana County, which is on the west, or in the east, in the Marsabit, there are water-related conflicts due to resource depletion. So how to solve and how to look how to address this problem. So what we did a lot of data collection, hydrological model development, and the hydrological model had two steps. There were lumped and distributed hydrological models available, built by us during the research. And based on these models, we can see all the inputs into the lake. We could compute the lake water variation, and then we could do scenario modeling, namely determining what will be the extent of lake surface area given different inflows, and of course the outflow is evapotranspiration. What you can see on the top part is considering the Omo basin that is the most upstream to the lake and that has a 90% inflow to the lake. And in the lower part, we have added two more treatment around the lake, the well and Cario, and we were looking to the inflow into the lake. Well, the main problem is that there are no measurements to determine what are the exact discharges and to calibrate such a model. For that, we have used remote sensing data, and this is where I can show you the type of remote sensing, the globally available data that it is available on precipitation, potential evapotranspiration, land cover, soil maps, and of course, digital elevation models. Different data set, a different spatial resolution, and where is a source from where they can be freely downloaded. Based on this data, we could build a hydrological model, we can build a lake water level variation, and we backtrack discharges from measured water levels. So looking at measured water levels, we could backtrack what will be the discharges coming into the lake, and we can calibrate and validate the level. This is a result you can see due to the lake modeling. You can see the simulated shoreline based on our models, that it is red line, and you can see the lake extent that comes from remote sensing. And you can see that there is a pretty good match between the two, which shows that even in an area that doesn't have enough data, data coming from remote sensing can help you a lot in determining what is the lake extent and the water volume in the lake. The other part that we were looking with remote sensing data was specifically for water-related conflicts around the Turkana lake. And this is an MSc research work of Krishna that used the remote sensing data to characterize the availability of natural resources, look how these resources are depleted, try to look at the relationship between availability of natural resources and the conflicts that are there in the area, and to address the vulnerabilities. All the analysis is carried at the level of settlement around the lake. So here also a lot of data, all the data was used from remote sensing, the land cover from Copernicus, the precipitation data, the NDVI, the soil moisture, and the evapotranspiration, and for that, a different spatial resolution and temporal resolution, and all were also a Python was used to analyze the data. Let me show you a bit the analysis of the precipitation throughout the years that was used, and what you see is also the precipitation where it was and what was the data and how much precipitation was. And you can see there were drought years through the analysis from 2017 and to 2022, while in the same time there were wet years in 2019 and 2020. So all this analysis was done based on the remote sensing data. In the same time, an NDVI data extracted was analyzed for the same area, and again you can see a substantial decline in the vegetation after 2020, while in 2018 and in 2020 there is a good vegetation cover in the same time. Similar conclusion was drawn for the soil moisture in these years. And what I want to say that by looking at these three components, one can determine the area where there is a depletion of resources. And one can see that there is indeed a movement of the population outside of the area where there is depletion of resources. All the data has been integrated in a dashboard that shows the water points that are there, the conflicts, and especially this remote sensing data based the natural resources depletion and the modeling of the lake water levels. The dashboard is publicly accessible, and we, as this is recorded, we will also put it in the end in the chat so that if you are interested to see the dashboard. With that, we covered very briefly the work using remote sensing data, and I will start the topic of artificial intelligence for water resources. It's a very new fancy word, and everybody uses it in the last 4 or 5 years, but we have applied artificial intelligence methods in hydroinformatics since 1995. And we applied it in PhDs, and around 2005, almost 70% of the MSc studies were with methods from AI, but now we are balancing and applying other hydroinformatics methods, not only AI. And what I want to mention is that we only may use machine learning from the AI spectrum machine learning algorithms. However, I will show you a component using AI that it is not machine learning driven. So looking at the floods, what we do simple visual comparison. On the left side, you can see from the Dartmouth register what is an image from MODIS of a flood and how does it fit with what was actually recorded from flood. You can see the blue and red, and all this was an inundation map in Tanzania. It's very simple to do the visual comparison. But there are moments when this is really complicated. What you see on the right-hand side is actually a part of the Danube Delta. It's called Fonta Fortuna part in Romania, the Danube Delta, where it is very difficult to see the differences between what is modeled, what was registered. So we propose to look at flood extent as a shape using the Hausdorff distance as a new metric, and this is something from the artificial intelligence. All this research work was done with a PhD student, Taine Asuntao, within the SENT project. So quickly about the flood metrics, we are used to use flood metrics that are based on ratios, and they are looking at different ratios between the observed and simulated flood, if they are matching or not matching, or they are not simulating or not observed. And there are many types of metrics, but all these metrics are not looking at the time component. They are metrics at a certain moment in time, and they are simple ratio. Doesn't tell always a lot about the flood if you don't have the image and the extent in front of you. So because the spatial temporal accuracy is important, we looked into the possibility to use the face recognition softwares that it's called Hausdorff distance, and to see if we can characterize as a metric the flood extent. What we are proposing, it's a modification of that distance, and we are including, these are complicated, not so complicated formulas that are looking at the distances between important points, and we are actually introducing a river and looking at this distance for a river and flood extent. In order to see what are the results we are obtaining, the experiment that it is done usually for benchmarking flood modeling softwares is that you have an area that it is with a lot of depressions, and they are, and there is a discharge hydrograph inflow that comes here in the top part and floods the area. If that flooding happens between 30 minutes and 12 hours with different roughness coefficients, this is how the flooding would look like. And now we have computed 30 minutes how these metrics will capture or not flood. And you can see between capture and non-capture, the classical metrics are capturing very well the flooding. But in the same time, the ones that we have proposed with outdoor distance, these are the 6 ones, 3 of them are capturing very well. As you go in time, you will see that towards the end of the simulation, the classical metrics are only 3 of them out of the 8 available will capture this characterization of the flood extent, and the other ones are not. While the outdoor distance is still capturing very well, it's actually improving as the time passes. This was what we tried as an experiment. So with this, I will give the floor to Claudia, who will continue with the IA component in a totally different area. Thank you, Claudia. The floor is yours.
Hello, everyone. Thank you very much, Ioana, for the introduction. And yes, let me just share my screen. Maybe it's easier. Yes. Is it good? Yeah. Okay. Thanks. So today I'm going to talk about how we can enhance climate services using artificial intelligence. And first of all, let's start with talking about what are climate services and why we need them. So climate services, according to the definition of the European Commission's roadmap for climate services, they cover the transformation of climate-related data together with other relevant information into customized products, which can be projections, forecasts, and information, which are used to counsel on the best practices, development, and evaluation in relation to climate that may be useful for society at large. And climate services providers develop science-based and user-specific information related to past, present, and potential future climate, assisting the society in adapting to climate variability and change. So basically, what is the key message here is that the end users, which are usually in our case water managers, can use information about present and future climate thanks to these climate services. And why do we need climate services? Well, as you can see here on the left map, you have on the left side of the slide, you have a map with the number of natural disasters that were reported between 2000 and 2019. As you can see, unfortunately, they're quite high numbers. And also, as we can see in the right side of the slide, this number of disasters have been increasing over time. So if we compare the years 1980 to 1999 and the consecutive 20 years from 2000 to 2029, we see that there was already a big increase, and this increase in the frequency of this event is expected to even continue in future climate projections. And also, of course, related to the number of events, we see that there are a lot of people that are affected by these natural disasters. And as we can see on the bottom, the majority of people are affected by weather and climate-related extreme events. So this is to show why we need to have appropriate information about weather and climate forecasts. So now the point of we understood why climate services are needed, but then why do we need to improve them, and why do we need to use artificial intelligence for it? So in general, policymakers and the stakeholders need good quality data, and this data can be observations, forecasts, and climate projections. And but the problem is that forecasts at the moment are not always accurate, and this happens especially for specific lead times, so specifically horizons, which are the subseasonal, so let's say around up to 1 month ahead. And this is because of physical and computational limitations of the numerical weather prediction models that are being used. And why can we improve it with AI? Because AI can provide forecasting models that are capable of handling large amount of climate data, And the computational costs are very high in the training phase, so in the calibration phase, but once the model is calibrated, then they are the computational costs are very low in the operational phase. Also, in general, the genesis of extreme events is not very well understood in many cases, so we still don't know why some of these extreme events are happening, and then we can use AI to discover some hidden relationships between climate and weather variables. And finally, we need information about climate and climate change and extreme events that are tailored for the end users who might not be technical people sometimes. So we need to tailor this information. And for instance, sometimes the information that we have about climate and weather is not provided in the spatial or temporal resolution that is needed or in an easily understandable format. So AI, for instance, can help downscaling this information and provide specific variables required by the end users. So what I'm going to show you now are the results of some of the results of the Horizon 2020 project called CLINT, which has as a main objective to develop an artificial intelligence framework composed of machine learning techniques to improve climate science in the detection, causation, forecasting, and attribution of extreme events. And the project in total has 4 big case studies, as you can see here, and we are analyzing different extreme events, which are drought, tropical cyclones, heat wave, and warm nights, and compound events. But IHE is mainly focused on droughts and is mainly focused on 2 case studies that you can see here, the Douro Basin in Spain and the Rhine Delta in the Netherlands, of course. So what is the approach that we follow in our projects to enhance with AI the climate services? First of all, we go in consultation with the end users and stakeholders of our local case studies, and we investigate which are the existing climate services there, what are the needs for improvements, and what are the impacts of the extreme events in the local case studies. Then, based on this information, we try to develop machine learning or AI in general model to improve the forecasting. And for today, I will show you some results about the subseasonal stream flow forecast with long short-term memory models. And finally, we assess the value of these AI-enhanced climate services. So we want to see if the forecasting at the local scale is actually improved or not. I'm going to talk very little about the case study of the Douro River Basin. So in this case, we are actually, we want to forecast the inflow that is incoming to the Barrios de Luna Reservoir. And this reservoir is upstream the Orbigo system, which has the 90% of the total water storage of the entire system. And this reservoir is providing water for agriculture, domestic use, and cattle industry. And it is a multi-purpose reservoir because it's both providing water during the dry summers, but also flood control during the wet winters. And the important thing is that the total water storage that is offered by this reservoir is very similar to the annual water demands, which means that this reservoir is very prone to have issues if there are water shortages. So what we did, what actually some colleagues did, Celia, she's a PhD student here at IHE, she had some interviews with the stakeholders to know what were their problems, and what they found out is that the stakeholders at the moment are not using any kind of forecast. They have some, let's say, guess from previous years of how much a period is going to be wet or dry, and the stakeholders actually need to know how much inflow is expected in the next month to plan the reservoir operations. So what we did was to develop a machine learning model, well, deep learning if you want, based on a long short-term memory model, which is suitable to capture long-term dependencies in time series and has been used quite a lot now for rainfall runoff modeling. And we use a combination of observed and forecasted precipitation and temperature. So the observations were provided in situ from Spain, and the forecasts were the open source of ECMWF extended range, which go up to 30 days ahead. And so we use these inputs, we develop our model, then we obtain our results, and we assessed the performance by comparing our results with the observations, but also with the climatology, and we computed the NEC metric. So in terms of the machine learning model, the LSTM, we actually developed 5 different models. One targeting a different lead time. So 4 models are actually targeting the accumulated inflow in 1 week. 1, 2, 3, and 4 weeks ahead. And the other one, the 5th model, is actually forecasting the accumulated inflow of the next 28 days. And what we see here is that we use a combination of the observed and forecasted input. We merge them as they were only one time series, which is a bit uncommon for the LSTM. And we feed it into our model, and then we obtain our forecast. So here you can see the results of our forecast. Maybe they're a bit small, sorry. You can see the different weeks in the 4 upper quadrants, and then the monthly forecast. And what we can see is that the LSTM forecasts, which are the continuous line, the green one, they are way more similar to the observations than the climatology, which is the information currently used. And also what we can see is that, of course, with when going ahead with the lead times, the forecasts are getting worse, but this was to be expected also because the quality of the meteorological forecast has the same characteristics. But also if we see at the monthly lead time, monthly aggregation, we actually have way higher improvement with respect to the climatology. And we are now in the phase of actually showing these results to the stakeholders and of the case study and see what they think about it. And from my side, it's all. So thank you very much. And I will give the floor to Haris now.
Thank you, Claudia. I will share my screen now. Okay, hello everyone. So today I will be talking about a small catchment which is in the Netherlands, and it's a part of the Eiffel project, Eiffel project. The catchment is Ahoverijs, and we will be looking towards the climate effect on this catchment and how we have strategized the nature-based solutions based adaptation strategies to mitigate some of the effects of the climate adaptation. So looking towards this catchment, so it's a transboundary catchment which is shared between the Belgium and the Netherlands, and most of our work is focused for the Netherlands part of the catchment. Currently, the catchment is facing surface and groundwater bans because of the intensive agriculture activities in this catchment. So the economical activities in the catchment is highly dependent upon the water availability there. So before looking into the adaptation strategies, we wanted to know like what will be the situations in the catchment in the coming years. For this, we get the data of the future projections from the KNMI. And then based on this data, we compared the present decade, which is 2010 to 2020, with the future projected data for the 2050. And we came to know like the rainfall in the summer months is going to decrease. And on the same side, the potential ET due to increase of the temperature is also going to increase. So in the coming years, the situation is going to get worse based on the results of these projections, and catchment will be underwater stress in the coming years. In order to address these challenges, there is a growing interest in the stakeholders in the area towards the natural nature-based solutions, and So, and there is also a growing interest that on the scientific, like how we can use the nature-based solutions to adopt to the droughts in the future. So we focused on the nature-based solutions for this research, and some of the questions or the research questions that we were looking into were how we can spatially analyze the area where these nature-based solutions will have a positive impact, how we can model them, and how we can quantify the results of these nature-based solutions in a mean that it can be easy to communicate with the stakeholders, how they are going to perform in the current situations, and how they are going to adopt under the climate change. For this analysis, we develop a hydrological model. We use MikeSheet modeling tool for this purpose. And then this MikeSheet modeling tool have a different components. And then from this, we can know what is happening over the surface, what is happening in a river in terms of discharge. We can also look into the subsurface what is happening in the subsurface and also in the groundwater. For this, we used a combined data. Some of the data we used were locally available from the water board, and as the catchment is a transboundary, to have synchronization between the Netherlands part of the catchment and the Belgium part of the catchment, we used land use and digital elevation models, which is global products. We were also looking into the land use for the future as well, and where we use the artificial Malus tool, which is based on the machine learning in order to see how the land use is going to be changing in a coming future in this catchment. After developing this model, the next task was to test the different nature-based solutions. For that, we shortlisted in consultation with the stakeholders what they think can be a possible solutions that can be implemented in an area. Then we shortlisted 6 of them. The first one was the wetland restoration. Other one was the heathland restoration. The next one was the infiltration ponds and also the tree plantation and the small ditches blocking. So in order to model them, we were looking into the different components of the model. So in the literature, if you look, so most of the modeling is only based on the vegetation, changing in the vegetation properties, or either they are changing the roughness or the detention. But for this study, we were also looking into how this nature-based solutions is going to affect the soil organic content. And because of the change of the soil organic content, how the soil hydraulic properties are going to be changed. And for the analysis of the effect, we were looking into the different layers of the system. And we designed key performance indicators, which are the surface water availability, soil moisture index for the unsaturated zone, and then the groundwater availability for the groundwater. And we set the threshold based on the results to see if the water level is going below 20% threshold, then it will be a complete ban of the water abstraction for the irrigation purposes. The same is for the groundwater. So we put each of this measure into the model, which is here on the top line here. We modeled each independently into the MikeSheet using the parameters that I showed you in the previous slide. And we were looking into how this individual is going to affect the groundwater availability into the system. We were mostly because of the droughts, we were mostly interested in looking how we can retain more groundwater into the catchment, so it can be used in a summer period. And because of the more groundwater availability, the base flow to the river in the summer period can be more. So we put each of this measure into the MikeSheet model, and then we excluded the tree plantation and brook bed barrier because they were not having a positive impact on the groundwater availability. In the end, there is also some areas identified by the water board and the province where they want to have this kind of green measures activities. So we limit our final strategies based on these 2 maps, and only if there is a conflict at like if 2 measures have a positive impact at one cell, so we were looking which measure is going to give a more positive impact and recommending that over that area. So based on this, we have 2 strategies, S1 and S2. So if we look into the result of the strategy S2, so this pie chart is showing what is the current condition and how it's going to be in the future if we implement these strategies. And if we look into the SC, and we are seeing like the blue area in the pie chart is going to be increased, which is showing like there will be less band days in the catchment because of this strategy adaptation. And we also observe if we go from upstream to the downstream towards the outlet, so the effect of is summarizing, and we are having more good impact of these nature-based solutions towards the outlet side of the catchment. Just to emphasize more on this one, so there is a time series of this discharge at the outlet, and here the dark red are showing the band days, which will be under the climate change. And if we implement this nature-based solutions, then how it's going to be reduced, it has been shown by the light one. And then we are seeing like it's not going to be completely eliminated, but there is a much reduction in the band days. Similarly, if we look into the groundwater at the different points on the wells in the catchment, and we are completely looking into this again as we move towards the outlet, there is a complete elimination of the band days from the catchment, and the water availability can be ensured with respect to these nature-based solutions. All of these results have been put together in the shape of the web applications for communication with the stakeholder. And also it's freely available, and you can also have a look if you want to know more about these things. Moving towards the second topic of this discussion, and it is quite interesting because when we were using the IHE model for the climate analysis, we need to run the model again and again. And each time the IHE for each run, it was taking many hours, and it was creating a lot of data in a computational power. But for the climate analysis, maybe we want to run it many times for the sensitivity and uncertainty analysis of the climate data, and also to have the probabilistic climate impacts. So the solution is to develop a surrogate model, which will be the simplest representation of the IHE model. But the IHE involves many physical processes, where the processes are non-linear, and such kind of the non-linear relationships can be well captured by the deep learning algorithm. So we developed the surrogate model of the IHE using the deep learning techniques, but this is the work which is currently under progress. So we wanted to see like how well the surrogate model, deep learning based, can be used for the future unseen scenarios if we train it from the current results of the IHE. For this one, we get the input data. In addition to the meteorological data such as precipitation and potentiality, we also extract the DEM and surface roughness into this model. And we trained it from the results of the IHE with the discharge, actuality, and groundwater level. For the grid data, which is the actuality and the groundwater level, we use the CNN 2D in combination with the convolution LSTM. For the training of the actuality and the groundwater level. And for the discharge, we develop another completely different model, which is based on the LSTM. And surrogate model was trained for 2010 to 2019, but we evaluated the results to see how it's going to perform for the future. These are the results, how the model is performing in the actuality, which is quite good, and all the values of the kg is near in a good range. However, for the groundwater level, the model is having some difficulties in where the value of the kg is not good, and in the sum of the cells. The reason is that if you look into one of the series where the kg's value is not good, because the model has not, during the training period, the model has not seen such values which can be in a meteorological data for the future. So we are working how we can improve this to further. But LSTM, when we use the LSTM for the discharge prediction, which is it is doing quite good, and we were looking into the different sequence length, which is 30 days, 90, and 365, but the best results are coming when the sequence length is 365 days, and the kg in the Nash value is quite good. So this was all from our side. Your questions are welcome. And this is the detail of us. We are happy to answer any of your questions, and you can reach out to us. Thank you.
Well, thank you very much to all our guest speaker of today, Ioana, Claudia, and Harris. And we will proceed to the question that had been written in the chat. And the first question is from Ridwan Said, who says, request for missing monitoring or Gaussian data, how we can use RS data for model calibration and validation.
I hope that I understand well the question. So we use the remote sensing data for input and not for model calibration and validation. In order to do the model calibration and validation, we had to extract from the water levels of the lake and to deduct what would be the inflows into the lake. And then based on those inflows, we could see if the hydrological model, which was an IHE HMS model, is giving at the outlet the same discharge. So this is, I hope that this was the question. So
thank you. And the second question is the tool that is used for hydrological situation. Simulation, sorry.
Yes, so this is what I just mentioned, that we have used the US Army Corps of Engineers tool, that it is IHE HMS, that stands for Hydrological Modeling Systems. So this is a tool that we have used both in lumped and distributed form.
The next question is for Riban Said, and is how reliable is the meteorological data of remote sensing data? Or I suppose it is the question.
Well, that one has to check for the region from where the remote sensing data is downloaded. But you know that what we have used is data that has been rainfall estimates from both rain gauges and satellite observations. So it's only remote sensing data. This CHIRPS data is estimated from both rain gauges and satellite. So you really have to, for the region that you are using, you have to check and to look at what the rainfall estimates are. And it is case by case basis. Yeah.
Thank you. Here is Nikolai, who, I don't know, put questions. Precipitation, meteo station point data. I don't know what.
Well, it is downloaded the rainfall. It's downloaded graded rainfall estimates.
Is it acceptable to use it for research? I mean, RS meteorological data for data is scarce watershed.
Well, you always have to check what you are doing. You have to calibrate, you have to validate. And if there is no data somewhere, so you need to start from somewhere. And if there is globally available data available, I would say that one should start using it. And as time passes, also look and start collecting data and see how well the models that you are building are predicting what it is measured on the ground. So, if nothing is available, one should start from somewhere and really use the wealth of data available.
And it's also the common question of Siraj. Data is the main challenges in hydrological modeling. Your case, how these issues how are these, in your case, these issues considered?
Well, I think that I just mentioned that, you use data as a challenge, but one should look for the globally available data and see what is the outcome. Yeah.
Marcella Busnelli is requesting in the predictions of water levels in the lake, Did you also consider the groundwater exchange, and how?
No, we didn't consider groundwater exchange because there was no data available for the groundwater inflows. So no, the HEC HMS was in itself. We didn't have a groundwater exchange with the surrounding. No.
There is an interest of collaboration that I will send it to Ioana later by email, and also it is mentioned that it is needed advice whether to use regionalization methods or remote sensing data, such as geoglows of globe. Sorry for.
Yeah, well, I think that needs to be a case by case, and you need to look at the data, and you need to see how that data is for your particular case. So there is no one that can say this is better than the other. So it's a case by case, and you really need to analyze the data that you have available.
And here there are two questions that maybe we need to combine. One is there justification for the NSA value of the LSTM model to be better for 1 month's lead time as compared with 1 week lead time? And the other question is also connected with LSTM model, and it says, is unable to predict the peak flows, the performance is in its satisfactory way, and you may improve the forecast by using a complementary ANN model for modeling the errors.
Yes, thanks. So for the first question, to respond to Yirgalem, there is a reason on why the monthly forecasts are better than the weekly, and it's simply because it's easier, because there is less noise in the signal that you're trying to forecast. So in that sense, it's just an easier task. And the other question, yes, it's true that the model is not representing well the peaks. It's missing some of the peaks. Also let's say the intensity of these peaks, and we haven't thought of combining it with other models at the moment, and the reason is because the case study that we are interested in, the Douro, they are mainly facing droughts, and we actually conducted an evaluation of the performances on the low flow periods, so actually from spring to summer, and the performances were good. So let's say we said, okay, we recognize that our model is not perfect, but let's say that for our purpose was good enough, but it would be, yes, well, yeah, as you suggested, one option would be to combine it with other models for the error. And also, I think later you also gave the suggestion of going for post-processing, basically, to combine physically based models with AI to improve the quality. And yes, this is probably the most promising part in general. But we were curious to see from a research point of view how far ahead we can go with only meteorological information, so without post-processing the stream flow forecasts. And so there were also other questions later.
Yes, and Professor Gopakumar from India says, what could be the promising future developments in terms of artificial intelligence that could transform flood management and water resources planning over the next decades?
Well, I think that this is a very interesting question, and I think no one has yet the answer to it. So definitely we should look at always at a combination. We have to look at the physics always, and then we all know that the AI models are able to predict when nothing changes in the system. So they are very good for those who are maintaining and do decision in a system. But then when you really do designs and new elements in the system, you need to consider physically based models. However, regardless of the fact that there is no that they can be used very well for a decision in a system that does not have changes, we still should not ever forget about the physics and still use physically based models. So a hybrid approach, a combination, is what is advisable. But what would be in the next decades that we are all to learn about? Thank you.
Juan Chacon asks, from the work you have done, do better forecasts produce different decisions?
Yeah, thanks, Juan. It's a very good question, and we haven't tested it yet. So we just arrived at the results that you saw in the slide, and the next step is to actually use these results and put them into the what we call the user-based definitions of the extreme events, and then do this kind of what-if scenario. So, like if the managers had this information, like during the drought of 2022, for instance, would they have operated the lake, the reservoir differently or not? But this is still to come. Thanks.
Dilip Gotan mentioned if single model may not be adequate to generate a accurate forecast, are you considering using a conceptual model for process modeling and artificial intelligence model for the error modeling?
Yes, I partially responded to this already. So that's a strategy, a possible strategy. We are not doing it at IHE in our project because there is another partner who's doing that, and they are doing it at a pan-European scale. So we are also waiting to see the performance of the local scale. But I mean, from what we've seen in general, I can tell you that probably yes, the post-processing is one of the most. So like the correcting the error, the model errors can be one of the most promising paths for machine learning models.
Mobhab said that he has a few questions regarding the data use. Is the 30 MDEM data accurate enough for your analysis? Also, how you handle precipitation data? Was it solely derived from satellite sources? And if so, is this data freely available for use?
Thank you for the question. This is a recurrent question if is 30 meters DM is accurate enough. You always have to consider what do you have available, and if this is what you have available, you need to work with it. And yes, lately the data that it is available for downloading 30 meter DM or even less, they are quite accurate and they can be used. How did we handle the precipitation? We did download. It is downloadable. It's freely available to be used, and it is not solely from satellite sources. It's a data that it is estimated from both rain gauges and satellite observations. So this is.
Badru says, what will be the future of artificial intelligence in water management? Is that will replace us as a modeler?
Well, I think that we should all respond to this, but hello, Badrus. I know him very well, and he used to be our student, and good to see you here. Well, replacing us as modelers, aren't we, when we develop an AI model, modelers with AI? So how can this replace us as modelers? And I think that no model, no matter what a model does, there is always the need for interpretation of the results and for taking decisions or steps, what to do with the results that are coming out. So I think that they are not our replacements, they are our tools and helpers. But I don't know if anyone else has a different, do you want to? add?
Well, we have a few questions. We
questions.
had to accelerate, but how the countries from developing world, where there are many backdrops prevail regarding keeping the climate safe for living beings, can be beneficial from this model, and how this model can bring a significant change in improving the working situation of the climate.
Thank you for your questions. But in this, our research, we were only focusing what will be the impacts of the climate on with respect to the water, but we were not looking into the feedback. Will be the changes within this catchment can bring to the global climate scenarios. So that was not the scope of the research. And for that kind of analysis, maybe we need a bigger global scale models to do such kind of analysis.
Thank you. Thank you very much. How to generate hydrometeorological time series data for data scarce basin like upstream of Lake Turkana?
Well, I think that this is a recurrent question, as we have said, that this is time series that are downloadable from chips. So, yeah.
We continue having a lot of questions, so maybe I would like to invite Claudia, Ioana, and Harris to select the more important ones, because many have been answered.
There is one question related to the use of the remote sensing data for the big catchments and then how it's beneficial for the small catchments. So we have recently did the literature review on this one, and then we found that the use of the remote sensing data is mainly focused for the large catchments, and then there are very few studies which are focused on the use of this data on a small catchment. But the case study that I showed you, where I used the MIXI model for the development, it's a hybrid model, so it's using both the local data as well as the remote sensely based large data sets in it. So the performance of the model is quite satisfactory in this term, and then we can also use these big data sets in the small catchments as well.
And to conclude, I think there is a question to Maria. It says, there are certain participants identified as Maria. So, well, Maria explained in the beginning that you use all the same link, and that was with the same name, but you can always change the name. So that's the reason why there is the same name, which is nice.
Maria has learned something extra in this seminar that we can pick a final question, and I think it's time to conclude. Would you like to say something, Ioana?
Well, I think that all the following questions are more or less the same about the.
There was one about the surrogate models.
Okay, so please.
From Danilo.
There is one about the surrogate model. Here it is. I will read the question and you will answer. There is this, hello, Danilo, good to see you after, I think it's 5 years. The question is like that, how is managed, how the uncertainties are managed when surrogate models are used to generate data for training validation, and how are these managed, the uncertainties when surrogate models are used to generate data for training validating and models? I think that's the only part of the presentation that did not have questions so far, so this will be the last.
Yes, so we use the MIXI results in order to train the surrogate model. So we are not using the data from the surrogate models for the generation of AI-based models. So the surrogate model itself is based on this deep learning. And we haven't done this uncertainty analysis for this one, but it can, I guess it can be done by doing the uncertainty analysis of the MIC and then doing the uncertainty analysis of the surrogate model, and then we can see like how the uncertainty from the input data or training data is propagating to the outputs. But we haven't done it yet.
Well, I have to say thank you to all participants, that there has been a lot of interest for this seminar, as I have explained. Thank you for all the things learned and the fantastic sharings of our speakers, that I really thank you. And well, as you know, this is the last online seminar of this year. You are welcome for the next year series. And of course, you're always welcome to suggest ideas for the topics. So without other words, have a happy holidays and end of the year, and hope to see you next year. Thank you, Ioana, Claudia, and Haris and Vishay, that is at the back of us with all the technical issues that Maria has learned. Never share your personal link, so that to avoid that we all are named Marias. Have a good day, all of you, and thank you for your participation.
Thank you all.
Thank you. Bye.
And thank you, Maria, for inviting us.